Hello everyone here and out there. The topic of our study today is physics, which is a great tool to understand the creation of God, ranging from a small, tiny particle to all the way universe itself. The materials that I'm gonna discuss in this physics lecture series, you will be able to find those materials from a book called Beautiful Mathematical Laws of Physics. The book is not out there yet, but you will be able to find out all those information about this book, publication date, all those information about this book, simply by Googling the title of this book. And also you will be able to read few chapters of the book just simply by Googling the title of the book. Here's how the book cover look like. Here's how the book cover will be look like. Anyway, enough about the title of the book. So let's start by defining what physics is. Physics is not only the study of motion and its relation with rates, but also I forgot to highlight the rates, very important. We're going to come back to this. But also it's a study of mass and energy and their relation with space-time. All right. So these are very important. We're going to come back to this to understand it more, to understand it mathematically. So above definition can be divided by any integer n, but we're going to keep it simple. We're going to let n be 2. That means we can divide above definition of physics in two parts. One is classical physics, and number 2 is modern physics. Again, we can divide classical physics by any integer n, but as I said, we're going to keep the math, we're going to keep the thing simple. So let's divide it by 3. So we can divide classical physics in 3 parts. A, Newtonian physics, or mechanics, B, thermodynamics, all right, we're not going to add that, right? All right. B, thermodynamics. C, we can call it electromagnetism. Likewise, we can divide modern physics in 2 parts. A special theory of relativity, and B, I guess, quantum mechanics. So let's look at classical physics again. Classical physics is mainly, basically, the foundation of classical physics basically laid by the work of a single person, Sir Isaac Newton. Of course, other people contributed some extent, such as Michael Faraday and Maxwell, but it's basically mainly the work of Sir Isaac Newton. Likewise, modern physics is actually mainly the foundation of modern physics is kind of based on the work of Albert Einstein. Yeah, it is true that many other people help also contribute in modern physics, such as Max Planck, Heisenberg, Schrödinger, and Niels Bohr, but mainly modern physics is 90% of the modern physics is actually work of Albert Einstein, and 90% of the classical physics is actually work of Sir Isaac Newton. That's why many people consider him as a father of physics, and many people consider him as a father of modern physics. In this lecture, we're going to use some of the beautiful mathematical laws to understand all those main topics of physics. Today, our focus is going to be only on Newtonian mechanics. We're going to use 24 or 25 beautiful mathematical laws to understand everything of Newtonian mechanics. So what are the beautiful mathematical laws we're going to use to understand Newtonian mechanics? Let's see. Number one, let's see the number one beautiful mathematical laws we're going to use to understand the Newtonian mechanics. Number one is average velocity, which is delta D over delta T. Number two, acceleration, which is a vector quantity, so we can put a little arrow. What is vector quantity? We're going to come back and discuss more about the vector quantity. Now let me put the beautiful formulas first, and we're going to end up making examples, many examples, to understand how this formula actually make the physics very easy. So acceleration is delta B over delta T. Number three, maybe you can write distance formula. Distance formula is velocity, initial velocity. Let's write velocity final first. Velocity final is velocity initial plus acceleration times time. Number four, we can write the distance formula. Distance formula is simply D equal velocity initial time plus half AT square. What about the velocity final square one? That is velocity final plus 280. Number six, Number 6 formula we're going to use to understand the physics, to understand all those topics of physics, classical mechanics is, I guess, A. Simply acceleration. Acceleration is F force net force over mass. Number 7, I guess we'll be able to, let's put some vector quantity, Ax or Ay. So Ax is, we're gonna do all those examples to understand what this formula is all about. But let me write down the formula first. A cosine x, cosine theta, and A sine of theta. Number 9 is, I guess we can put frequency. Force of frequency is mu, and mu is a kinetic, mu is a constant of some object. We're gonna talk more about it when we make our own example to understand this formula. So mu times normal force. Number 10, what can we write number 10? Maybe force due to gravity, which is z m1 m2 over r square. Okay, so far we have 10. We're gonna write 14 or 15 more. Number 11 is z, which is F force due to gravity over mass. Number 12, maybe momentum, which is mass times velocity. Number 13, this is just momentum of a straight line. So angular momentum or other kind of momentum, we we'll discuss torque to understand the other kind of momentum. So torque is, which is forces vector quantity times r, which is also vector quantity. Number 14, what do we have? Maybe momentum before equal to momentum after. 15, let's write some formula for a spring. So spring, the force of a spring is K for constant and X. And X is the stretching or compressing of a spring. We'll discuss Hooke law to understand for spring, force of a spring. Number 16, maybe potential energy of a spring, which we can get simply by taking the integral of kx. Kx from 0 to x, which is half kx square. So half kx square. We'll go over basic math before we try to make all those examples to understand the physics, all those topics of mechanical physics. Number 17 is what equation we can write? Well, centripetal acceleration. What is the force of a centripetal acceleration? I guess F equal ma, centripetal acceleration. Number 18, what would be the velocity acceleration of a centripetal acceleration. What is the acceleration of a centripetal acceleration? It's simply b squared over r. Number 19, kinetic energy, I guess, half mv squared. 20, potential energy, which we can write as m mass times gravity times delta H. Delta H is just change of height. We'll make a lot of examples to understand that as well. Number 21, we have, what do we have? Number 21, maybe work. Work is force times distance, which we can write as energy, total energy. Number 22, we can say total energy is kinetic energy plus potential energy plus internal energy. Number 23, the last equation we're going to use today, last physics equation we're going to use today to understand all those physics topics, especially Newtonian mechanics, is power. Power is work over time, and we know that work is, we already defined what work is. Work is force times time over t, and force time distance is, we wrote it somewhere here, and that is distance over time. Distance over time is delta b hat. So f b hat. So that's the equation we're going to use. There's 23 equation we're going to use to understand what's going on in the Newtonian physics. Yeah, if you pay attention throughout the whole lecture, you will be able to understand everything. Should be able to understand everything in Newtonian mechanics, and will be able to answer any questions in the test. So let's go over the math part before I make the example of this physics equation. So let's go over some simple math problem.